Welcome to the deep dive. Our mission today, well, it's to cut through the noise, get straight to the core insights from a really interesting paper you've shared.
That's right.
We're diving deep into neural network architectures today, specifically one called MesaNet. It's from a paper titled MesaNet, Sequence Modeling by Locally Optimal Test Time Training.
Yeah, and it's quite fascinating. This isn't just, tweaking a knob on an existing model. They're proposing a new layer, a new way of thinking about processing sequences.
Sequences like text or time series data, basically anything where the order matters.
Exactly. And the goal seems to be tackling some of the limitations we see in current models, even the really powerful ones.
Okay, so let's try and unpack this. For this deep dive, I really want us to focus on maybe the more academic side. Like, what are the core technical ideas here, the innovations, and of course, how does it actually perform compared to things like transformers or other recurrent networks?
Sounds good. I think the place to start is this concept the paper keeps mentioning, optimal fast weight programming.
Okay, optimal fast weight programming. What does that actually mean in practice?
Right, so think about how most neural nets learn. They have what we usually call slow weights or parameters. These get adjusted really gradually during training, right? Using tons of data, backpropagation, it's a slow burn.
That's the standard deep learning training loop we all know.
Precisely. Now, fast weights, that's a different beast. Imagine a part of the network that can change its behavior, its parameters, almost instantly, while it's processing just one specific sequence.
So it's adapting super quickly to what it's seeing right now.
Exactly. Adapting on the fly. Now, the idea of fast weights itself isn't entirely new. People have explored this. But MesaNet, it takes a pretty significant leap.
How so?
Well, instead of just doing a kind of approximate update, like maybe a quick gradient step based on the current input, the Mesa layer is designed to actually compute the mathematically optimal set of these fast weights.
Optimal, meaning?
Meaning the weights that minimize some loss function, considering all the data points it's seen so far just within that single sequence it's currently processing.
Whoa, okay, so it's not just a quick reaction. It's calculating the best possible internal setting given the context it's built up for this specific sequence. That sounds like it could be really computationally demanding.
It could be, yes, but that's where the layer-specific design comes in. That's the core innovation, really. This mechanism lets it hold on to past information effectively while also adapting incredibly fast to the newest thing it sees. It's a purpose-built layer for this optimal online response.
Right, and this is where it gets really interesting for me because the paper explicitly says this new Mesa layer is an improvement on an older idea, right? A recurrent Mesa layer from earlier work.
Absolutely. They build directly on that foundation. That earlier concept, sometimes called the RLS or recursive least squares Mesa layer, had a big practical problem for modern deep learning.
Which was?
It wasn't parallelizable over time. Because it used a recursive calculation, essentially solving things step by step, you couldn't easily speed it up on GPUs or TPUs, which rely heavily on parallel processing. You had to finish step T before starting T+1.
Ah, a bottleneck for training. So the first big innovation here is fixing that, making it parallel.
Yeah, exactly. The new design is described as chunk-wise parallelizable. You can process chunks of the sequence together, letting it play nicely with modern hardware accelerators. This is crucial, for actually training these things at scale. It makes it practical.
Okay, parallelization, huge for scaling. What's the next big improvement they highlight?
Numerical stability. The older RLS method, especially if you wanted the model to forget older information quickly, could apparently become unstable. Numbers could blow up or vanish.
Right, that can happen with recursive updates sometimes.
Yeah, and part of the issue was how it handled regularization, which decayed too fast. This new version uses a different mathematical engine, basically. It uses an iterative method called the conjugate gradient, or CG, method to solve the core optimization problem.
Conjugate gradient, okay. How does that help stability?
It's generally a more robust way to solve the kind of linear system that pops up here. The paper calls this internal solver linsolve. It finds the solution iteratively, and it's much less prone to blowing up, even if the model is set to forget aggressively.
So it's like refining an answer step by step until it's good enough, rather than calculating a direct inverse, which might be tricky?
That's a good way to think about it, yeah. More robust. And that brings us to the third point, context-dependent forgetting.
Context dependent. So it's not just fading memory at a fixed rate.
Exactly. The layer has these learned gates, forget gates, and input gates. They're usually pretty simple, maybe just a single learned number, but they allow the model to decide at each step, based on the current input, how much of the past context is still relevant and how much should be, well, forgotten or downweighted.
Okay, so the memory management itself becomes adaptive, learned from the data, not just a fixed decay rule.
Precisely. It adds a layer of intelligence to how it manages that internal state. And then maybe the most distinct innovation, the one tied closely to the test time training part of the name, dynamic test time compute.
Dynamic compute, what does that mean for how the model runs?
Remember we said it uses that CG method to solve for the optimal weights at each step? Well, the number of steps that CG needs to take isn't fixed. It depends on how difficult the problem is right at that moment in the sequence.
Ah, so the amount of computation isn't constant, it adapts.
Yes. That's the really cool part, I think. You can set a stopping criterion, like stop iterating when the error is below this tiny threshold, epsilon. So for easy parts of the sequence, maybe it only needs a few CG steps. For complex parts where it needs to pull in long-range info, maybe it needs more. But critically, it only computes as much as needed for that specific token.
Wow. So the model effectively learns to manage its own computational budget, token by token. That's very different from, say, transformer self-attention.
Totally different. With standard attention, the compute cost grows maybe quadratically or linearly depending on the variant with sequence length, but it's a fixed cost structure for that length. MesaNet's cost per token can actually change depending on the content.
That seems like a massive potential advantage for efficiency.
It really could be. The paper shows results where using this dynamic stopping maintains performance very close to using a high fixed number of steps, but uses way fewer steps on average. Huge potential win, especially for long or variable sequences.
Okay, let's touch on the math just a bit. High level, you said it's minimizing a loss to find these optimal fast weights.
Right. At a high level, the goal is to find the fast weights, let's call them phi hat, that minimize a regularized loss function over the history of inputs, represented as key value pairs within the sequence. Equation 10 in the paper lays this out.
And doing that minimization turns out to be the same as solving a linear system.
Exactly. The paper shows it's equivalent to solving a specific linear system, and the components of that system are derived from these recurrent state variables, which they call GT and HT.
Ah, the memory states.
Yes. These GT and HT variables just get updated step by step using simple linear recurrence relations. So the layer keeps track of history in these states, uses them to build the linear system for the current step, and then uses CG, linsolve, to solve it and find the optimal response.
Got it. And there was that technical note comparing it to DeltaNet, saying MesaNet uses online Newton descent, not just gradient descent. Why is that distinction important?
Yeah, it's a bit technical, but it points to the optimization's nature. Simple gradient descent just follows the slope of the loss function. Newton's method uses second-order information, basically, the curvature of the loss landscape, which can often lead to faster, more direct convergence to the minimum. The HT matrix in MesaNet effectively encodes this second-order information. So they're saying it's implementing a more sophisticated type of online optimization within the layer itself compared to something like DeltaNet, which they frame as online gradient descent.
Okay, that paints a clearer picture of the mechanics. So the crucial question, how does it actually perform? Does all this cleverness translate into results?
That's always the key question, isn't it? The paper shows results on synthetic tasks designed to probe specific sequence modeling abilities, things like regbench and MAD, and on those, MesaNet does really well, often on par with or better than other modern recurrent models or even linearized transformers, and competitive with full transformers sometimes, so the core mechanism seems solid.
Good start. What about real-world tasks like language modeling?
On the Slim Pajama language modeling benchmark, they trained models up to nearly 1 billion parameters. And across different sizes, MesaNet consistently got lower perplexity, better prediction scores than comparable models like Mamba 2, XLSPM, and DeltaNet. It even beat transformer baselines of similar sizes in their setup. That's a pretty strong showing.
That is significant. Did they notice anything about where in the sequence it performed best?
Yes, that was interesting. They observed this trend where RNNs often do better early in a sequence and transformers maybe catch up or excel later. MesaNet seemed to extend that early sequence advantage further than other RNNs, suggesting its memory mechanism might be quite effective at leveraging the recent context.
What about long sequences? Length extrapolation is often tricky for RNN-like models.
They tested it out to 32,000 tokens. MesaNet showed pretty strong extrapolation compared to many recurrent baselines. It seemed competitive with other long context models, although they did mention some other specialized models still provide stiff competition. They also wisely added a caveat that perplexity alone might not tell the whole story for really long-range dependencies.
Fair enough. And beyond just predicting the next word, downstream tasks. reasoning, few-shot learning.
Generally, it held up well there too. On benchmarks testing things like zero-shot reasoning or recalling information from context, MesaNet usually matched or beat the other recurrent models they compared against. But it wasn't always better than the transformer baseline. For example, they noted it underperformed on translation tasks compared to the transformer.
So strong, but maybe not universally dominant across all possible tasks yet.
That seems fair. It suggests different architectures might still have strengths in different areas. Transformer attention might still be better for certain kinds of global information integration needed in translation, perhaps.
And did they explicitly test that dynamic compute benefit, show that it saves computation in practice?
Yes, they did, and the results looked promising. They showed that using that dynamic stopping criterion for the CG solver, letting it stop early when the error was low enough, gave almost identical prediction performance to using a fixed high number of steps. But crucially, the average number of steps actually performed per token dropped dramatically, something like from 30 fixed steps down to around 9 on average.
So same result, much less work on average. That's a concrete win.
Exactly. It validates that the dynamic allocation idea isn't just theoretical. It can provide real computational savings.
Okay, so placing MesaNet in the bigger picture, it seems like it connects to a lot of different threads in AI research.
It really does. The paper itself draws lines to several areas. One is models using stacks of simple, greedy learners, but applied here in a novel way for inference. Another is this idea of Mesa optimization.
Mesa optimization, that sounds related.
Yeah, it's the idea that the outer training loop learns an objective function that the inner, faster process, like the Mesa layer, then optimizes at test time. So the model learns what local problem it should be solving on the fly.
That's a fascinating concept, learning the goal itself.
It is, and it also relates to older ideas about defining layer outputs via optimization problems, things like energy-based models. But me and the closest relatives are fast weight programmers models that explicitly modify some weights very quickly. MesaNet just replaces the simpler update rules often used there, like Hebbian learning, with this provably optimal calculation.
And they mentioned dynamic evaluation too.
Right, dynamic evaluation is just the general term for models that adapt their parameters or state during test time based on the specific input. MesaNet fits squarely in this category, with the fast weights being implicitly updated by solving that optimization problem at each step. And as we discuss, they position it as using a different, arguably more powerful update mechanism online Newton descent compared to related work like DeltaNet's online gradient descent.
Okay, so wrapping this deep dive up, MesaNet's core seems to be this unique layer that finds the optimal fast weights for the current sequence history at every step that gives it this powerful adaptive memory.
And crucially, this new version is practical. It's parallelizable for training, it's numerically stable, it uses learned gates for smart forgetting, and it has this really unique dynamic compute feature, adjusting effort based on difficulty.
Performance looks strong, particularly against other modern recurrent models on language tasks and synthetics, with good length extrapolation too, even if it doesn't beat transformers everywhere. And the dynamic compute seems to offer real efficiency gains.
Yeah, it's drawing on some deep ideas from optimization and memory research, presenting a really distinct take on sequence modeling that goes beyond standard attention or basic recurrence.
What really stands out to me is that core idea, a layer that doesn't just apply a fixed computation, but learns how to optimally solve an internal problem tailored to the immediate input data right there at inference time.
Exactly, and that really makes you wonder, if models can learn to dynamically adjust their internal computations like this, what other ways could we design networks to adapt their structure or their problem-solving approach based on the specific instance they're facing? How much more efficient or capable could models become if they learn to allocate their thinking resources more intelligently? That feels like a really interesting direction to explore.
Definitely something to keep an eye on as these architectures continue to evolve. A fascinating look into MesaNet,